and welcome to the second lecture of Physics 401A. The topic of discussion for this lecture is the symmetries and Newton's laws. First, we have to understand what symmetry is. A symmetry is the property of invariance of a system before and after a certain operation. Let's consider, for example, a vertical cylinder, as you can see in this figure, and the cylinder, unless we make some artificial spot or some coloring, we can never understand whether it is rotated about its vertical axis by an arbitrary amount or not, because it always looks the same, right? This signifies the configurational symmetry of this uniform cylinder. Of course, if the cylinder is not uniform, it's deformed, it has several damages, it has colors, like this type of identifications, then we can distinguish. Other than that, we cannot. But let's say we have a perfect cube, also without any spot, without any damages, then the cube need not necessarily look identical when it's rotated about an arbitrary angle about this vertical axis. It only looks the same when it is rotated by particular angles, let's say pi by 2, pi, or 3 pi by 2, so multiples of pi by 2. So the cube has a configurational symmetry, but for particular angles. It's not symmetric under any arbitrary rotation, unlike the cylinder, who has a symmetry under arbitrary rotation about this vertical axis. Like these physical objects, or rather the configuration of these physical objects, we also can define symmetry for physical laws. For physical laws, the symmetry is defined in such a way that if the variables in this law of the physical or the physical equation under certain transformation does not change the equation as a whole, then the equation is said to be symmetric, or the law, physical law, is said to be symmetric under that transformation or modification. So in formal way, we can say a physical law is symmetric when its mathematical expression remains the same before and after a transformation of the variables. This type of transformation is generally called a symmetry transformation. Okay. For example, if let's say if in an equation dx dt is equal to x, if we just say that x is changed to x plus a, where a is a constant, then of course you can understand dx dt will not change, but x on the right hand side would change from x to x plus a. Then this is no longer a symmetry transformation for this equation. On the other hand, if you say x is now transformed to 2x, then dx dt is equal to x, basically is a symmetry transformation, okay, because it is just a multiplication by a factor 2 on the both sides of the equation, and the final equation remains also the same, right? Now here in the current context, we shall only discuss whether Newton's second law, which is the only law of evolution, among the three laws of Newton, is whether this is symmetric or not under usual space-time transformations. So the first space-time transformation is known as the translation in space. What is that? So let us first understand that r, which is the instantaneous position vector or the position vector of any particle under consideration, with respect to an origin, pre-assigned origin having coordinates 0, 0, 0, okay, then we can simply write the Newton's second law like this. M d2r dt2 is equal to f. This is a vector equation, so it has three components, you know. Now, if we define a new coordinate system with a new origin at A, of course A is a vector having components ax, ay, and az, okay, and A is a constant quantity. So if we just define, if we just shift the coordinate system by a constant amount, okay, then the current position vector will simply be r prime, which is equal to r minus a. You can simply see the analogy of this to the so-called center of mass frame, which we discussed in the last lecture. Right? That was also a transformation or the shift of origin. Okay. Under that condition, you can see, so a is a constant vector. So basically you can see that all the components, let's say x prime will simply be x minus ax, y prime will be y minus ay, and z prime will be z minus az. Right? Now you have this one which is always true because this is a constant quantity. So if you differentiate this r prime by once or twice with respect to time, then you simply have this equality always. So if we in addition suppose that mass is also unchanged with the change of origin, okay, which is true for any non-relativistic mechanics, you can easily understand that mass is not a function of the motion of the body in non-relativistic limit, then you can always say that m prime is also equal to m, and combining these two, this one and this one, finally you can write this. Okay, so the left hand side of the Newton's second law is basically the same before and after the transformation. Okay, now whether the right hand side is equal or not, we don't know. So this is the f, and f can be in general a function of r, dr dt, which is the velocity, and time explicitly. Now we know as a is constant, dr prime dt is equal to dr dt, no problem. T prime is equal to t because nothing is to affect the time here. But the r prime is now r minus a. And then you can say that the new force, if the force is always acting in the same, it is only the coordinate axis which is shifted, or the total system which is shifted, both are equivalent. Okay, the force can now be written in terms of the prime coordinates, and you can see now instead of rvt, it will now have r prime plus a v prime t prime. Okay, so here you can see that this is not exactly the same type of functional dependence, right? There is a which is coming. So it therefore seems that the force expression has been changed. But what happens, the good news is that in reality, for all the usual forces, the space dependence is not really the dependence on its current position absolutely, but the dependence is on the relative distance, and that's very crucial. Relative distance between which points, which 2 points? The point particle which is responsible for the force and the point particle which is experiencing the force. We will call them respectively by the source particle and the test particle. Okay. And in a case where you have just two mass particles and we are talking about gravitational force, you know that the famous Newton's law of gravitation gives you like this, where basically this is the function of the relative distance of r2 and r1. Okay, and this analogy, in an analogous way, you can say that for two charged particles you have Coulomb's law of attraction or repulsion, okay, which is also depending on the relative distance between two charges. Then you can easily say that this force, which is now a function of not r prime but actually r2 prime minus r1 prime, which is eventually for this type of forces which we have talked here, is simply depending on r2 minus r1. Voila, so we are done. So f prime is equal to then f. So we had left hand side which was unchanged before and after the transformation, and now we have right hand side which is unchanged before and after the transformation. So if before the transformation Newton's law was valid, then after the transformation N2L is also valid. That's why we say that under space translation, for usual type of forces, depending on the relative distance of the 2 points, N2L is symmetric under space translation. Okay. Now you can see that all the four fundamental forces, fortunately, they all are depending on the relative distance between the source and the test particles. Okay. Now electromagnetic force has two components, one is electrostatic, one is magnetic part. So the magnetic part is not really easy to understand because there is a velocity depending part, but you can easily understand here the velocity dependence doesn't really play any crucial role in affecting the whole thing because velocity does not change here. Okay, so we are done. Okay, another thing is that sometimes we say that we shift the origin, sometimes we say that we shift the system. It's actually equivalent. Whether you are shifting the origin or you are shifting the system by a constant amount, this is always equivalent. Also, I mean, only thing is that you have to keep in mind that the shifts should be in the opposite direction to be in consistency. Okay. Now the second thing is that how they are behaving under special rotation. Whether N2L is also invariant under an arbitrary rotation of the system in space? Well, we will check. So let's say in an equivalent way we say that the system is fixed, it's not rotated but the coordinate system, coordinate axis is rotated by a constant angle theta. Okay, and now from unprimed position the new coordinate system has gained its primed position. Okay, and you can see that if the old x and y components for one let's say vector, the position vector of this point P for example is r, then in the old system this was the x component was small x and y component was small y. In the new system they are respectively x prime and y prime. By using simple trigonometry you can show that they are related by this relation. You can try this at home. This is very, I mean, basic exercise. You can do it. I hope all of you have done this in the high school. Okay. Now, since the source particle is at origin, that means at O, the force vector is also emanated from origin because the source particle is responsible for the force. Okay, but it is not necessarily always along the path joining O to P. It can be along any direction. If it's really along P, then it will be a central force. Otherwise, it's a general force. But whatever its direction be, I mean, that will be a vector and the vector will transform under this rotation of this coordinate system in the same way as the position vector transformed, right? So the x prime was x cos theta plus y sin theta. So fx prime is fx cos theta plus fy sin theta. And the same thing for this, y prime is equal to minus x sin theta plus y cos theta. And fy prime is minus fx sin theta plus fy cos theta. Again we assume time and m, they do not change under rotation. Nothing to do with this transformation. Then simply we can write the x component of Newton's law after the rotation in the new coordinate system. You can easily write this. M d2x prime dt2, m cos theta d2x dt2 plus m sin theta d2y dt2. We have just replaced the value of x prime in terms of x, y and theta, and then basically by classifying, basically by grouping those this unprimed part m d2x dt2 and m d2y dt2, you can simply again recognize them to be fx and fy. And you can simply see that fx cos theta plus fy sin theta is nothing but fx prime. So the x component of the mass times acceleration of the particle is equal to the x component of the force in the new coordinate system or the rotation, the coordinate system after rotation. The same thing we can show for y component. So vectorially this is also true, and which simply says that if you have a rotation about some axis, then Newton's law, Newton's second law is invariant under this rotation. and this is leading to the isotropy of space basically. In some lectures we will come back to this, and we will actually see that PCLM, I mean the principle of conservation of linear momentum, is the consequence of homogeneity in space, and principle of conservation of angular momentum is the consequence of isotropy of space. Okay, and that will be discussed in the context of very famous Noether's theorem. You will see that symmetry, conservation, all are related in a very elegant way. Now the third translation or transformation, this is the translation in time. That means we make a shift in the time coordinate without making any change in the coordinates. Okay, that means we are trying to do our experiment, let's say, at the same space, but let's say instead of today we will do tomorrow, or we did it yesterday. This is the thing. Now whether this changes the physics or not, that is the question. So if we do that, if you can start from this, so t will be t prime, which is t plus a. Okay, again t is translated by a constant amount, right? And r is to r prime, and which is exactly equal to r. So nothing to worry about this. So d2r prime dt2, by doing this chain rule of differentiation, you can simply show that. I have shown it in details. You can have a look later. You can simply show that this is exactly equal to d2r dt2. Okay, so the acceleration does not change. Yes, so N2L is invariant under time translation only if the right hand side is unchanged. That is our conclusion, of course, because the left hand side we shown this is unchanged, and m is also independent of time, so mass is also unchanged. Okay, so we have to check whether the basic forces are independent of time or not. And fortunately, again, the good news is experiments show, and fundamental theories are also there to show that all the fundamental forces in nature, they are independent of time. Hence, we don't have to worry about this time translation symmetry of N2L. They are in general invariant under time translation. Okay, but if we, let's say we have a system where we create artificially a force which has an explicit time dependence, let's say a time dependent periodic force, which is given by F is equal to F0 cos omega t n cap. Okay, then this force is not time independent, but for this specific one, if you do a constant translation in time, then this adds just a constant phase to the original forcing term, so that will not change the dynamics maybe, but in general, if it has a more complex form, a time dependence or something, let's say if it is like a 1 plus t square, this type of thing, then t to t plus a can change the dynamics. Okay, so time translational symmetry can be broken where the force has an explicit dependence on time. Okay, so in the next subpart of the lecture, we will discuss some other transformations and symmetry under those transformations. Thank you very much.